How you doing, Year 10s, and welcome to another video. Just make sure that when you watch these videos you have a pen, pencil and a highlighter, and make sure that anything you see on the screen must be written down in your booklets. After you've watched the videos, it's good technique to go and have a read of the textbook to make sure that you've covered off everything. Now let's get into the video. Unit 1, the periodic table. What is the structure of an atom? So we need to know what is inside an atom. The centre of the atom is called the nucleus, and it contains two subatomic particles, protons, which are positive, and neutrons, which have no charge. Electrons orbit the nucleus in these regions called shells. Protons and neutrons may be referred to as nucleons because they live in the nucleus. Protons are given the symbol P, neutrons are given the symbol N, and electrons are given the symbol E-. So the subatomic particle of a proton, it's found in the nucleus. It has a charge of +1 and it's given a relative weight of 1. Neutrons are found also in the nucleus. They have no charge associated with them and they have a relative mass of 1 as well. Electrons, they're found in the shells that orbit the nucleus. They have a charge that is exactly opposite that of a proton, so -1, and they're so small that we say that they have a charge of 0. Now we need to be able to represent atoms in a very specific way so that we can work out number of protons, number of neutrons, and number of electrons. So we have this convention where we have X, which is the symbol for the element. We have A, which is known as the mass number. And we have Z, which is the atomic number. And we can represent every element using that convention. The mass number is equal to the number of protons plus the number of neutrons. So basically how many nucleons the atom has. The atomic number is simply the number of protons of that atom, and that can be found directly from the periodic table. So for example, we have uranium 23592, so the name of the element U, that's uranium. The number of protons is the atomic number 92. To work out the number of neutrons, what we'd have to do is get the mass number and take away the number of neutrons. So it would be 235 take away 92, which is 143. 143 neutrons. The number of neutrons can be very different to the number of protons. However, the number of electrons in a neutral atom would be the same. So atoms of the same element always have the same number of protons, but some of them can have a different number of neutrons. If something has a different number of neutrons, it's described as being an isotope. The definition of an isotope is an atom with the same number of protons, but a different number of neutrons. So technetium, for example, has 3 common isotopes: technetium-97, technetium-98, and technetium-99. That's its 3 mass numbers. And if we were to write those according to the convention, well, they're all technetium, so they all have 43 protons, but then their mass numbers differ. So we have 97 Tc43, and then we have the 98 and the 99. The interest in chemistry is it's used in medicinal chemistry, and it's good for diagnosing certain diseases. Now the electrons fill the shells in a very ordered fashion, and we need to know how these electrons fill the shells. So the first shell, the K shell, can hold 2 electrons. The second shell can hold 8, the third shell can hold 18, the fourth shell can hold 32. So any shell, if we were to work out any shell, the number of electrons would be 2n squared. Now we need to follow some really concrete rules about how to fill those shells. So this is something that you might have done in Year 9. I'm going to draw a few of the electronic configurations of a few elements, and we're going to put the electrons in the shells. So for example, beryllium, it has 4 electrons and 4 protons, so we need to fill the shells. So 4p in the nucleus, I've put the neutrons in here, but it doesn't necessarily matter. Let's just put the protons in from then on. And now I need to fill those 4 electrons. So in the first shell, I can have 2 electrons. Now these 2 electrons will be paired. Electrons will try and pair themselves up. In the second shell, I can fit 8 electrons, but I don't need 8 electrons, I just need 2 electrons. Now the electrons will only pair when they're forced to pair. So these 2 will be separate and the electron configuration will be 2, 2. Neon has 10 electrons, so that means it will have 10 protons in its nucleus. In the first shell can hold 2 electrons. Those 2 electrons will be paired. In the second shell can hold 8 electrons, and that's how many electrons neon needs. So as I go through, I put 4 electrons in because they won't pair, and then the other 4 electrons will come in and pair with the first 4 electrons. It will have an electronic configuration of 2, 8. Potassium has 19 electrons, so this is getting a little bit more complicated. The first shell, it will have 2 electrons. Those 2 electrons will be paired. That shell is full. The second shell can hold 8 electrons, so this shell will be filled as well. So I go through and unpair my electrons and then pair them up with the remaining 4. I move into the third shell, which can hold 18 electrons, but before I can put in all of the electrons, I can only put in 8. So I go through and put in my 8 electrons, which gives potassium a stable outer shell. Even though it can hold 18 electrons, before I can add the extra 10, I need to put 2 electrons into the fourth shell. I need to do that because I can never have more than 8 electrons in the outer shell, or the valence shell. So I have to put 1 electron in this case in the fourth shell before I can start to put anything back into the third shell. So the outer shell in potassium's case only has 1 electron. Its electronic configuration would be 2, 8, 8, 1. The outer shell having 1 electron. So after element number 20, after calcium, they become a bit more difficult. Because we can't put more than 8 electrons in that outer shell, in that third shell, without putting 2 electrons in the fourth shell. Once we put 2 electrons in the fourth shell, we can then add the rest of the electrons, those 10 electrons, into the third shell. So there's a very important note there. We have to put 2 electrons in the fourth shell before we can fill completely the third shell. So vanadium, for instance, has 23 electrons. So it will have 23 protons. So the first shell will be full. It will have 2 electrons in the first shell. The second shell will also be full. It will have 8 electrons in the second shell. So that's 10 electrons in total. So I've got another 13 electrons that I need to fill. So I move to the third shell. The third shell can hold 18, but I need to apply the rule. I can only add 8 electrons at the start. So here I am adding my 8 electrons to the third shell. To make it stable, I have to add 2 electrons to the fourth shell. So here's my fourth shell with my 2 electrons. Now, that allows us to fill the rest of the electrons into the third shell. And vanadium will have 3 extra electrons go into the third shell. So its electronic configuration will be 2, 8, and then I've left a blank 2. And then if we go through and count, well, we've got 8 plus the 3, which gives us 11. We always have to have those 2 electrons in the fourth shell, and then the rest of the electrons can go in the third shell. So for nickel, if we look at nickel, then we can simply apply a little bit of a strategy. we have 2 electrons in the first, 8 in the second. Let's leave our blank for the third shell and put our 2 electrons in the fourth shell. Then we know that the remaining electrons must be in that third shell. So 2 and 8 is 10, and an extra 2 is 12. We need to fill up 28 electrons, so how many must there be in the third shell? There must be 16. So nickel has 16 electrons in the third shell. We can apply the same kind of principle to iron. Iron has 26 electrons, so it will have 2 in the first shell, 8 in the second shell. The third shell will just leave blank, put our 2 electrons in the fourth shell, and then we can go back and work out how many electrons are in that third shell. So 26 take away 12 is 14, so iron has 14 electrons in the third shell. The third shell is filled up by things that are in the transition metal elements. So where did this theory of the shells come from? Well, it come from what we call flame tests or emission spectra. So when we put certain atoms into a flame, we get a number of different lines in what we call a spectrum occurring. These lines are certain energy levels. They're called photons. Each different photon releases a different amount of light. And basically, each of these photons are small packets of energy, and the energy is being released from the electrons jumping down the shells. So atoms or electrons become excited when they gain heat from a Bunsen burner, for instance. They gain the heat, they become excited, and when they're excited, they're unstable. The only way that they can release that energy and become stable again is to release it in the form of light. So what will happen is if we have an electron in the K shell, for example, it could gain some energy and become excited and move 3 shells away. In this excited state, it's unstable and it wants to release its energy. So the way it does that is it starts to drop down from its excited state back to what we refer to as its ground state. And as it does that, it releases different amounts of energy. So to jump to the third excited state and then all the way back down, that's a lot of energy, so that might be a blue. Blue has a lot of energy. If it goes from the third to the first, well, that might be a little less energy, so that might be a green. Going from the first to the K shell, well, that's a fair bit of energy as well, and that's usually found in the ultraviolet section. But any of these electrons where they're moving from one shell to the other, it's going to release a certain amount of light. And we see that in the emission spectrum as those lines on that black background.
Thanks for watching, guys. Don't forget, drop a like on the video, subscribe if you're new, and I'll see you next time for episode 2.